Hello students, let us discuss hyperconjugation or no bond resonance. Okay, it is also a permanent effect. In a last video we already came to know permanent effects. In that we discuss inductive effect, resonance effect. Now another permanent effect we have hyperconjugation. It is also called no bond resonance. Okay, why it is called no bond resonance, that I will discuss later. Okay, how here what is hyperconjugation means? Hyperconjugation is a general stabilizing interaction. What is a stabilizing interaction? That I will go for the example. It involves delocalization of sigma electron of CH bond of an alkyl group directly attached to an atom of unshared system or to an atom with unshared p orbital. It is about permanent effect. Now what is the entire meaning of this sentence? I will go for the example only, then only you will come to know what is the meaning of hyperconjugation. Here for hyperconjugation, to say in a molecule is it there or not mean, first here you should come to know sp2 carbon should attach it to sp3 carbon. Okay, then only you can see the hyperconjugation. Okay, here important noting means what? sp2 carbon should attach it to sp3 carbon, then only hyperconjugation is possible. Okay, let us go for the example now. Here, so for example you have the CH2. Okay, if its cation is there, then here, okay, I will go for the, let us see here you have for example CH2, okay, having the positive charge, and after that you have the CH3 group is there. Okay, so here if you see for this carbon, what is the hybridization here? sp2. Okay, why it is sp2 means we have 3 sigma means sp2. Here we have 4 sigma, isn't it? It is a sigma 1, sigma 1, sigma, sigma. 4 sigma means it is a what? sp3. Okay, now so here for hyperconjugation sp2 carbon should attach it to sp3. Now what is the sp2 shape is what? Trigonal planar. Here you can see sp2 means we have the 3 bonds are there, trigonal planar. So once it's a cation means we have the one empty p orbital will be there, isn't it? Okay, now this is the condition sp2 carbon. After that here we have another carbon. Here we have the 3 CH bond, okay, and 1 CC bond is there. So this is the one sp3 carbon. So for hyperconjugation is what? This is the word sp2 carbon is attached to sp3 carbon. Okay, the condition is satisfied. Now sp2 carbons having the what? When one it is having the one empty 2p orbital of carbon. Okay, we have one empty 2p orbital in the carbon. So what happened? Because of empty p orbital here, the electrons of CH bond here we have one more CH bond. It was to go to stabilize this positive charge or electron to this p orbital. Okay, so here in CH3 CH2 plus nothing but ethyl cation, in which the positively charged carbon atom has an empty p orbital. This is the what here. This is the positive charged carbon having the one empty p orbital. One of the CH bond of the methyl group can align in the plane of this empty p orbital, and the electrons constituting the CH bond in plane with this p orbital can then be delocalized into the empty p orbital as shown in figure here. So this is the CH bond, isn't it? Okay, one sp3 methyl group having the what? Here one CH bond is there. So the electron of this CH bond will be delocalized, means they are going to shift. Okay, so this is called hyperconjugation. Here you have to, one thing you have to identify that here we are shifting the sigma bond. Okay, here just only one stabilizing interactions only. Okay, it is our stabilizing interaction, not the complete transfer. Okay, so there is a interactions what this want to stabilize the this p orbital which is having the empty. Okay, so here you can see the definition. So hyperconjugation is a general stabilizing interaction, so it is going to stabilize. Okay, it involves delocalization of sigma electrons of CH bond. Okay, Up to now, if you see the resonance structure, what we are doing, either you are shifting the pi bond or you are shifting the lone pair of electrons on the heteroatom, isn't it? But now in this case, what happened, you are going to shift the sigma electrons of CH bond of an alkane, okay? So an alkyl group directly attached to an atom of unsaturated system or to an atom with the unshared p electron. Simple here, alkyl group nothing but having the what sp3 hybridization will be there, okay? Now unsaturated system means what here, for example, just now told here CH2, if it's a double bond, okay? If it's CH2, if it is attached to here, let me write it clearly. So anyhow, I will go for the example later. So either it answer system, what is the example I will go later. An atom attached to with an unshared p electron, nothing but here carbocation. If it attached like this, what happen? Hyperconjugation is possible. Simply you are going to shift or delocalize the sigma electrons of CH bond, not the pi bond, not the lone pair of electron. This is a specialty of hyperconjugation. Okay. So next I will go for the next and the example. So here this type of overlap stabilizes the carbocation because electron density from the adjacent sigma bond helps in disappearing the positive charge. Here you can see, okay, this is a condition example. This is how we have carbocation. Carbocation means sp2 hybridization is there. So having the one empty p orbital, okay. So here what happened? Here we have the on this carbon we have the one empty p orbital will be there, okay. So what happened here? I am labeling this carbon and hydrogen. For this carbon I am labeling the hydrogen as a 1, 2, 3. Okay. As you know very well, sp3 having the what shape is a tetrahedral. So once the tetrahedral, what happened? Sometimes here, now for example, now in this case, now what happened here, you can see here we don't have any bond, okay. So these sigma electrons are shifted to this carbon atom, okay. So what happened while shifting means you can see here double bond is formed, okay. Here we don't have double bond. So this bond here, this bond is shifted to here. So what happened here, in between these two carbon we have the double bond. Here it's not there, but after shifting we have double bond. Here we don't have any bond, okay. So and sometime what happened, now labeling as this first, second, third, okay. So now first CH bond is stabilized. Sometime what happened here, so this is second hydrogen, this is a third hydrogen. Now so this bond is shifted to in between these two, okay. But here you got the double bond because of shifting of these electrons. So okay, next third case, what happened now in this case, now here first, second, third, now this bond here bond is shifted, okay. So because of that you got the double bond. So sometime what happened, sometimes this hydrogen, sometimes this hydrogen, sometimes this hydrogen. So you are writing the resonance structures with the showing like this H plus on the each resonance structure. So that's why it's calling as about no bond resonance. Here you can see, by writing the structures you are not writing any here bond between, here we don't have any bond, here we don't have any bond, here we don't have any bond. Simply you are writing what happened. So the shifted electron, while shifting the electron, here what happened, you are going to get the negative charge, the negative positive, you are going to write the double bond in between these two, and you are going to write the H plus on each hydrogen atom, okay. So that's why it's calling as about no bond resonance, okay, no bond resonance. Next, greater the number of alkyl groups attached to the positively charged carbon atom, the greater is the hyperconjugation interaction and stabilization of cation. What is the meaning of here means? Already we came to know. Here we have this is called tertiary carbocation. This is a what? Secondary. This is a primary. This is a methyl cation. Okay. Among this is the most stable. Why? Because means this having the positive charge and empty p orbital is there. Now this is a methyl group. What tendency to give the electrons? Okay. So more electron rich. Three members are able to give, 3 donor groups are there. That's why it's more stable. In this case what happened, we have only 2 donor groups. In this case we have only 1 donor group. Here we don't have any donor groups. That's why it is a least stable. Now according to that previous concept I discussed. Now same thing, how you are going to explain with hyperconjugation now means. Now if you see here C plus, okay. So once a C plus means here aberration is what? sp2, okay. For hyperconjugation is what? Our condition, sp2 carbon should attach it to sp3, okay. Here, okay, this carbon having the sp3. Next, again here, okay, I will go for the next sheet. So for hyperconjugation here, we are talking about the tertiary carbocation. Okay, it is attached to 3 methyl groups. Okay, isn't it? Okay, this is the first methyl group, and this is the second methyl group, and we have the third methyl group. Okay, here we have the 3 methyl group. Simply there we have the structure like this, isn't it? Okay, so if it is attached to only 2 methyl groups, here we have the 2 methyl groups. Okay, this is called what? Secondary carbocation. Here we have the hydrogen. So here what? Here this is a sp2 carbon. Okay, what is the condition for us here? So sp2 carbon should attach it to sp3 carbon. Now this is attached to, here we have the sp3 carbon, here this is also sp3 carbon. Why? Because means we have 4 sigma bonds. This is also sp3 carbon. Okay, it is attached to 4 sigma bonds. Okay, so in all these cases you can see the hyperconjugation. Now what happened? sp2 carbon, here this may be hydrogen bond, this bond may be shifted. So first hydrogen, this is second hydrogen, sometimes this bond may be shifted, sometimes this sigma electrons can be shifted. So 3. Here also condition is satisfied now, so I am labeling as this is a 4th, sometimes this is also possible, this is a 5th resonance structure you can write, and sometimes this one means 6th, sometimes this one 7, 8, 9. Okay, so here how many resonance structures possible? 9, means 9 CH bonds are ready for donating the charge electron to this carbocation. So 9 resonance structures you can write. So this is the what? Most stable resonance structure. Why? Because mean 9 sigma bonds are available to satisfy this carbocation. Okay, now let us see if we go for the secondary carbocation. So secondary carbocation means what? This carbocation is attached to only 2 carbons. Okay, so this is one methyl group. Okay, here we have the another methyl group. Now it's attached to only hydrogen. So this is secondary carbocation. Now if you see the resonance structure, this is the what? sp2 hybridization carbon. Why? Because it attached to only 3 sigma. Now this is what? sp3. Okay, this is also sp3. Now our condition is satisfied. What? sp2 carbon should attach it to sp3 carbon. Now resonance structures are here. This sigma CH bond is possible. So first one, this is second, this is also possible. This is also possible. 3 over. Next this one. Here 4th one, this is also possible. 5th one, this is also possible. 6th one. So total how many are there? 6 resonance structures you can write. So here in the case of now tertiary, what happened? On 9, here only 6 CH bond. So because of that reason, tertiary is compared to tertiary, secondary somewhat less stable. So like that you can go for the, if you go for the primary, if you go for the primary means what? This carbocation should attach it to only one methyl group. Okay, one carbon. So remaining what we have? Hydrogen, hydrogen. Now this carbocation attached to what's hybridization? sp2. Now this is the sp3. Now how many CH bonds possible here? This is a 1 bond, this is 2 bond, this is a 3rd bond. Okay, this is not possible. Our condition is what? This sp3 attached carbon, it from like this should be there. Okay, not directly attached. Okay, so now here we can write the what? 3 resonance structures we can write. So only 3 CH bonds are available to satisfy this positive charge. So because of that reason, what? Primary is less stable. Okay, now if you see the methyl carbocation now, so methyl carbocation means what? Here we have H, H, H. Okay, here do we have hyperconjugation? No, it is not there. So what is our condition? sp2 carbon should attach it to what? sp3 carbon here. Okay, here we don't have another carbon. So here hyperconjugation is not possible. So there is no shifting of CH sigma electron. So because of that reason, methyl carbocation is what? Least stable. So this is the order of stability. Okay, I hope you understand why we are telling tertiary is more stable, then secondary, then primary, then least we have the methyl carbocation. Here we don't have hyperconjugation in this case. Okay, so in the hyperconjugation, what I told you can what it may be sometimes what unsaturated compounds also you can see. Here you can see delocalization of alkenes by hyperconjugation in case of alkenes. Here alkene nothing but unsaturation. So if you see the alkene here, if you write the structure clearly, okay, here this is the structure. If you write here, this is the first carbon, second carbon, third carbon. Okay, so here I am writing the structure. So here we have double bond. Again here we have the one CH. Okay, this is the first, this is the second and third. Now this is the carbon what? sp2 hybridization. Why? Because means it attached to 3 sigma. This is also here one more should not be there. Okay, this is a sorry, this only we have only one hydrogen should not be there. Why? Because means exceeding valency. Okay, make it correction. This is only one H. Okay, so here already this is one bond and here we have two bond, one CH means valency over. So again here what? sp2 carbon. Now this is what? 4 bonds, 4 sigma bonds are there. So sp3. Now where you can get the hyperconjugation mean? In this area. Why? Because means sp2 carbon should attach it to sp3, isn't it? Okay, so now hyperconjugation, if you see here, so this is the what? First carbon, this is the second carbon and this is the third carbon. So this is first, second, third. So here you can see, here we have the p orbital will be there, and from the p orbital the CH bonds what can be shift here, means from here to here there is a shifting of electrons. Okay, sigma electron. So this is a orbital diagram showing hyperconjugation in the what? Propene. Okay, here there are various way of looking at the hyperconjugative effect. One of the way is to regard CH bond as possessing partial ionic character due to resonance. The hyperconjugation may also be regarded as no bond resonance. Means what here? For example, here, okay, this is a propene. Just now we already discussed sp2 carbon. This is also sp2 carbon, and this is a what? sp3 carbon. Okay. So our condition is what? sp2 carbon should attach it to sp3 carbon. So condition is satisfied. Now let us see how the hyperconjugation is possible means. So I am labeling as the first carbon, the second carbon, third carbon. So once if electron shifted to this carbon, what happened? This carbon going to get the positive charge. Okay. So now this positive charge, what happened? This positive charge may be compensated with this hydrogen and this hydrogen. Okay. So now first here third hydrogen shifted. Okay. Third hydrogen shifted means what happened now? Here this I have the positive charge. Now once electron shifted means you can see the bond here. Okay, here you can see now. So once here we have CH here, CH is there. Okay, once the electron shifted here means what happened now? This carbon going to get the positive charge. Now here this is going to get the negative charge. Okay, CH. So this is the first carbon, second carbon, third carbon. First, second, third. So this positive charge what? Going to compensate with the this CH bond. First, second, third. We have 3 CH bond. Now shift one electrons here. What happened now? So this hydrogen going to get the positive charge. Now this is the hydrogen here. Both are same. Okay. So now H. Here we have H. Then H plus. Then here you are going to get double bond and CH. Here you are going to get the C minus and H. H is there. Okay. This is the structure. So like this, sometimes what happened? This is a here I am labeling as this is a water. So sometime now this first hydrogen over. Next the second. Here the second hydrogen shifted the electrons. Okay. Next this is a third hydrogen means here third hydrogen. Okay. This is the first, second, third. First, second, third. So shifting of electron will be possible. Okay. So in this case first hydrogen, in this case second hydrogen, in this case third hydrogen. And you can see there is a no bond here. Okay, so that's why it's calling as a what? No bond resonance. Here we have in text question, that is what? Problem number 12.19. Why the tertiary carbocation is more stable than, here we have the what? Secondary. This is a primary. Okay, primary and least with the what? CH3 plus nothing but methyl carbocation. Here, as already I discussed just now, hyperconjugation interaction in tertiary carbocation is greater than the methyl ethyl cation, and here as the Tertiary carbocation has a 9CH bond. Already I just now discussed. Here we have the 9CH bond. And in CH3 what happened? Vacant p orbital is perpendicular to the plane in which CH bond lies. Hence the cannot overlap it with, and the CH3 lack of hyperconjugation. Simply what happened here? So in this case we have only 3 are there resonance structures. In this case we have 9. In case of methyl we don't have any hyperconjugation. So once the hyperconjugate structures are more means more stability. So here tertiary carbocation has the more resonance structures, no more hyperconjugate structure. That's why it is having the most stability.